In the last lesson, you learned about challenges with large language models. Starting with this lesson, you will learn how to deal with these challenges. By the end of this lesson, you should be able to explain what is in-context learning, what is context window size, what is prompt engineering, how prompts are tuned, and what is prompt chaining. You should be able to explain what is transfer learning, fine-tuning, and the difference between fine-tuning and pre-training. As a designer of generative AI applications, your responsibility is to ensure that model consistently generates factually accurate and unbiased responses to prompts. The successful accomplishment of this objective renders the model grounded. The process of achieving model grounding involves the application of a set of techniques referred to as conditioning. These techniques encompass precise prompt crafting to guide the model towards generating high-quality responses, as well as fine-tuning the model using specific data sets. Next, I'll introduce you to the conditioning techniques. Conditioning techniques may be broadly put in two categories: inference time and retraining time. At inference time, guidance is provided to the model in the prompts. Prompt engineering refers to the prompt design practices used for guiding the model. Prompt chaining involves breaking the prompt into smaller prompts that are used for generating model responses sequentially. A pre-trained model can be trained further on a specific task. In the context of transformer models, this type of training is referred to as fine-tuning. Fine-tuning involves retraining a pre-trained model. Human feedback loop is the same as fine-tuning, except that humans review the responses and provide feedback during fine-tuning. Keep in mind that these techniques complement each other and are not mutually exclusive. Let's dive deeper into each of these techniques. Before I get into the prompt engineering, let's talk about the foundational element of prompting, the prompt itself. A prompt may be thought of as composed of multiple building blocks. Instructions tells the model about the task you would like it to perform, or it may tell how to perform the task. For example, you can tell the model to act like a 5th grade science teacher. Input data is a task-specific input. For example, it is a question in case of Q&A. It may be content of a PDF document in case of a summarization task. In this example, it's a question. Models can make use of examples to produce better responses. In addition, models learn from the context. This inherent ability of models is used to prevent hallucinations and imprecise responses. In this part of the prompt, you provide additional information on the task. In this example, I'm asking the model to operate under a specific context. Last part is the output format. You can guide the model to produce output in a desired format. This is extremely important as the output from the model is generally consumed by the application before it is presented to the human. For a moment, let's zoom in on examples and the context part of the prompt. Earlier I mentioned that models have this inherent ability to learn from prompts. This phenomena is referred to as in-context learning. It is the model's ability to temporarily learn from the prompt itself. This knowledge is not permanent and has no impact on model's parameter weights. As a result, this temporary knowledge is referred to as non-parametric knowledge. Model generates responses using both parametric and non-parametric knowledge. Prompt engineering techniques may be put under two broad categories. First one is prompt tuning. Prompt tuning involves carefully crafting prompts that guide the LLM towards a specific task or desired output. Now, there are multiple task-based practices that are applied to achieve this goal. To give you an idea, in the prompt, you can teach the LLM to solve a problem by sharing examples. Within the prompt, you can force the LLM to think through the steps to solve a problem. We will dive deep into these and many more practices. Retrieval augmented generation, or RAG, is used specifically to address the missing context challenge that I discussed earlier. The idea is to augment the prompt with the enterprise context to address hallucinated and imprecise response challenge. The context is retrieved from some external system or storage such as vector database. One important aspect to keep in mind for both these techniques is that maximum size of the prompt is fixed by the model's architecture. As a result, the amount of information that can be passed in the prompt is limited. The maximum prompt size is known as the context window size. It is measured in terms of number of tokens that the model can accept as input. Larger context windows are always desired, but it all depends on the model. For example, GPT-3 model supports a maximum of 2048 tokens, whereas the GPT-4 has a context window size of 32,000. One learning from here is that context window size of the model is one of the criteria for the model selection. Next, I'll explain prompt chaining by comparing it with single-step inferencing. In single-step inferencing, you would create a single large prompt and use it as input to the model, and the model will generate the response. In prompt chaining technique, you will break the prompt into smaller parts. Then you would pass the smaller part as input to the model to generate a response. This response will then be combined with the next prompt and passed as input to the second model. The final response is produced by the last model in the chain. This technique has demonstrated favorable outcomes for enhancing the performance of language models, particularly in terms of response accuracy and correctness. Additionally, it proves to be highly effective in mitigating challenges associated with LLMs. There are two broad categories of fine-tuning techniques. Domain adaptation results in a model that can carry out multiple tasks in a specific domain. For example, a publicly available model is not trained to be an expert in the field of medicine or law. With domain adaptation, you can train the model on medical data or law data to become proficient at multiple tasks within these fields. Instruction fine-tuning is geared towards training a model to become proficient at a specific task. It involves use of labeled data. Examples of instruction fine-tuning are summarization and fraud detection. In fact, in the past exercises, you've already used multiple fine-tuned models trained to perform efficiently on certain tasks like question and answering and summarization. Both pre-training and fine-tuning involves training, but there are differences. Let's go over these differences. I'll start this conversation with an analogy. Pre-training is like attending a comprehensive school before specializing in a particular field, and fine-tuning is like applying the acquired general knowledge and skills to specialize in a particular field. Focus of pre-training is on building the general knowledge, whereas the focus in fine-tuning is all about specializing a pre-trained model for a specific domain or task. You need considerably less amount of data for fine-tuning. For example, GPT-3 was trained on 450 billion words, but it can be fine-tuned with less than 100,000 words depending on the task. Training time is much longer for pre-training. For GPT-3 with 175 billion parameters, it took 34 days using 1024 GPUs, costing approximately $4.6 million in compute alone. For simple tasks, fine-tuning can be completed within a few hours. The performance objective for pre-training is to achieve good performance across multiple tasks, whereas with fine-tuning, the performance objective is to make the model excel in a specific task or a specific domain. When it comes to adaptability, fine-tuned models are restricted to one task and they cannot be adapted for any other task. In this lesson, I covered multiple concepts that you need to understand for building applications that can address the LLM challenges I discussed earlier. You learned about the model conditioning techniques that are applied at the time of inferencing. Prompt is designed and tuned using prompt engineering practices. Retrieval augmented generation or RAG is used for augmenting the prompt with context retrieved from external sources of data. Prompt chaining breaks the prompt into smaller prompts and carry out inferences sequentially. Prompt engineering is enabled by a phenomena called in-context learning, in which the model acquires temporary knowledge from the prompt. Models can be fine-tuned to become good at certain domain or specific tasks. Although both pre-training and fine-tuning mechanisms are similar, their goals are very different. Human feedback loop involves a human to provide feedback as part of fine-tuning. Fine-tuning is enabled by transfer learning phenomena, in which models extend their knowledge by building on the existing knowledge. Starting with the next lesson, we will dive deep into each of these conditioning techniques. Happy learning, and I'll see you in the next video.